We focus on ruling out closed orbits. So let's assume that based on some numerical evidence or our own intuition, we think that a particular system has no periodic solutions. So how can we establish that the system indeed has no periodic solutions? We will briefly outline three methods for ruling out closed orbits. One is gradient systems. Number two is Lyapunov functions. And number three is Dulac criterion. So let's look at gradient systems. Suppose the system can be written in the form x dot is equal to minus del v for some continuously differentiable single valued scalar function v of x. Such a system is called a gradient system with potential function v. Note, suppose that x dot is equal to f of xy and y dot is equal to g of xy, then x dot is equal to minus del v implies f of xy is equal to minus dv dx and g of xy is minus dv dy. So there is a theorem which states that closed orbits are impossible in gradient systems. We observe that in fact most two-dimensional systems actually do not turn out to be gradient systems. Recall that all vector fields on the line are gradient systems. Let's consider an example. Show that there are no closed orbits for the system x dot is equal to sine y and y dot is equal to x cos y. The system is a gradient system with potential function v of xy is equal to minus x sine y, and we can readily verify that x dot is equal to minus dv dx and y dot is equal to minus dv dy, and so by the above theorem there are no closed orbits. Now we discuss a Lyapunov function. Consider a system x dot is equal to f of x with a fixed point at x star. Suppose that we can find a Lyapunov function, i.e. a continuously differentiable real valued function v of x with the following properties. 1. V of x is greater than 0 for all x not equal to x star and v of x star is equal to 0. So v is positive definite. 2. V dot is less than 0 for all x not equal to x star. So all trajectories flow towards x star. Then x star is globally asymptotically stable in the sense that for all initial conditions x of t tends to x star as t tends to infinity. In particular, the system has no closed orbits. The rough intuition is as follows. All trajectories move monotonically down the graph of v of x towards x star. So let's visualize this through a figure. So that's the equilibrium point x star, that's the graph of v of x, and the trajectories move monotonically towards the equilibrium x star. These solutions actually do not get stuck anywhere. If they did get stuck, then v would actually stop changing, but by assumption v dot is less than 0 everywhere except at x star. So how can we actually construct a Lyapunov function? Unfortunately, there is no systematic way to construct a Lyapunov function. So let's consider an example. By constructing a Lyapunov function, show that the system x dot is equal to minus x plus 4y and y dot is equal to minus x minus y to the cube has no closed orbits. Consider the function v of xy is equal to x squared plus ay squared, where a is a parameter which we will choose later. Then v dot is equal to 2x x dot plus 2ay y dot, which is equal to 2x times minus x plus 4y plus 2ay times minus x minus y cube, which is equal to minus 2x squared plus 8 minus 2a times xy minus 2a y to the 4. So now we can choose a is equal to 4 and the xy term will vanish, and we are left with v dot is equal to minus 2x squared minus 8y to the 4. So we can easily check that v is greater than 0 and v dot is less than 0 for all xy not equal to 0, 0. Hence, v is equal to x squared plus 4y squared is indeed a Lyapunov function, and so we do not have closed orbits. In fact, all the trajectories approach the origin as t tends to infinity, and so the system is in fact globally asymptotically stable. So now we discuss Dulac's criterion. Let x dot is equal to f of x be a continuously differentiable vector field defined on a simply connected subset R of the plane. If there exists a continuously differentiable real valued function g of x such that delta times g x dot has one sign throughout R, then there are no closed orbits lying entirely in R. Unfortunately, there is no systematic way of finding g of x. Let's consider an example. Show that the system x dot is equal to x times 2 minus x minus y and y dot is equal to y times 4x minus x squared minus 3 has no closed orbits in the positive quadrant xy greater than 0. So let's go ahead and pick g is equal to 1 divided by xy, then del dot g x dot is equal to d dx, g times x dot plus d dy, g times y dot is equal to d dx times 2 minus x minus y divided by y plus d dy of 4x minus x square minus 3 divided by x is equal to minus 1 upon y, which is less than 0. Since the region xy greater than 0 is simply connected and g and f satisfy the smoothness conditions, so Dulac criterion tells us that there are no closed orbits in the positive quadrant.
Now, when we have a model of the real world, it's quite useful to know if we can actually rule out closed orbits. So in this lecture, we outlined three methods that can be useful for ruling out closed orbits. Number one was gradient systems. So you show your system is a gradient system. The second is based on the method of Lyapunov functions. And the third was based on Dulac's criterion. Now, all these three are very, very powerful theoretical ideas, and when they work, they can be very powerful, except that the only issue is that trying to get them to work in practice can be slightly tricky because there is no real systematic procedure on, for example, how you might construct a Lyapunov function. So it's nice to know that these methods exist, but it's also nice to keep in mind that in practice they sometimes can be a little tricky to use and to actually show for your real world model. Nonetheless, they're extremely powerful methods which you should be aware of.